Welcome to the intimate gathering of people interested in advanced topics in NSX. My name's Bruce Davey. I'm a principal engineer in the Networking and Security Business Unit. So I'm going to be talking with you for the next hour about advanced and forward-looking things in NSX. I worried a little bit about this title because every once in a while you'll do a talk on advanced topics and people will say, oh, that wasn't advanced enough. I don't. At the same time, NSX is kind of new, so I don't want to leave people behind by assuming you all know it all. So I'm mostly going to do a little bit of recap of the fundamentals very quickly, and then I'm going to sort of talk about really where the platform is going. So this is more advanced in terms of like it's forward-looking rather than advanced in like you need to be a rocket scientist to understand it. But if you do understand everything I say, you should pat yourself on the back because obviously you picked this session because you're smart enough to come to an advanced session. So I hope you all go out of here satisfied. We do have microphones in a couple of places there. I like to take a couple of questions during the presentation. If I take 60 questions, I don't need to do the presentation at all, so I probably won't do quite that many questions, but you can ask questions during the presentation if you want, and I'll take a couple and then hopefully have time for a few at the end. But please do use the microphones so that everyone can hear you. And I was in this room on Sunday, and not everybody had a good audio experience, and apparently it was somewhat location dependent. So if you're finding the audio isn't quite to your liking, you may just want to try moving. There's a lot of space on this side of the room in case you're in a dead spot or something. But hopefully you can all hear well. Person in the very back corner there, can you hear me okay? Just wave if you can. Okay, got at least one thumb up from the back row there. Jolly good. All right, so let's get underway then. There's a disclaimer, forward-looking, etc. So here's what I would like you to get out of this session. I hope you'll go away understanding some of the latest and greatest things we're doing in NSX. Some of the things I'll talk about are already shipping. Many of them are actually in production, or sorry, in development. I'm in the engineering organization. Way back in the dark ages, I was actually a researcher, so I've always worked on things that are a little bit further out. So we'll be talking a bit about what's here today, but a lot more about what's coming. And so you'll get some insight into the future direction of NSX. And hopefully you just go away with a more solid understanding of what network virtualization is really good for and what value it delivers. And hopefully you'll get that from other sessions too, but I do want to try to spend a little bit of time talking about why network virtualization is a worthwhile technology. And of course, it's not necessarily that everybody needs it. So as I think I said a year ago, if you go out of here convinced that you don't need network virtualization with a technical basis for that decision, that could actually be a useful investment of your time. I'm not going to aim for that goal, but it could happen. Okay, so here's what I'm going to do. I'm going to recap network virtualization very briefly, not because I think you haven't seen it before, but because I just wanted to get us all on the same page and stress the things that I think are really important about network virtualization before I launch into the deeper stuff. Then I'm going to cover really four main technical topics. I'm going to talk about what we're doing to tie together physical networks into virtual networks. This is something that I've put a lot of personal energy into, and it's a really important part of our product, and we have a lot of work going on there, so I'll talk about that at some length. I'm going to talk a little bit about some of the work we've been doing around new encapsulations, partly because traditional networking people just love to talk about encapsulations. How many people would call themselves a traditional networking person? Okay, maybe a third of the audience. I would put myself in that category. I've just been doing virtual networks for about 2.5 years since I joined Nicira, but my much longer background was on doing traditional networking. So we'll talk a little bit about how we encapsulate packets for network virtualization and what we're doing in a forward-looking way there. And one of the things we're enabling through this work on encapsulation is some ideas around service chaining, which is, I think, a pretty important topic as we start looking at what network virtualization is good for. And then at the very end, I'm going to spend a few minutes talking about what we're doing to enable network virtualization across multiple sites. Today, if you look at most of our deployments, people have virtualized individual data centers. And we have a few multi-site use cases that are working today, and we're looking to expand the total set of use cases that we can cover in the multi-site environment. So I'll give some quite high-level and forward-looking stuff about multi-site use cases and how we're tackling them. Okay, so this is my one-slide summary of network virtualization. And as we've done in the past, I like to define network virtualization by analogy to server virtualization, focusing on a couple of very specific properties of server virtualization. When you virtualize a server, you start with a physical machine, and you have a certain set of fairly broad requirements for that physical machine. It has to be x86, it has to have a certain amount of memory and so on, but it's quite broad requirements. And then we put a hypervisor layer on top of that physical machine, and then we are now able to run software replicas of the physical machine in a completely decoupled way from the underlying hardware. It's so decoupled that we can move those those software replicas to other places or swap out the hardware and put in new hardware. So the first thing that we do in virtualization is to decouple the services and the applications from the underlying hardware. That's the first point that I want to make that I will apply to network virtualization. The second point is that when you virtualize something properly, you end up with a very faithful reproduction of that thing you virtualized. So a virtual machine completely reproduces all of the properties of a physical machine. It has the same instruction set, it has memory, it has I/O, it has networking. All the things that you expect to find in a physical machine are present in a virtual machine. This is distinct from, say, something like memory virtualization, where you get your own address space, but you don't get, say, your own disk. So the idea of decoupling and faithful reproduction is the idea that we are really stressing when we talk about network virtualization. We start with a set of hardware resources, networking equipment that has very broad requirements. The basic requirement that we have is that we can forward packets from one place to another by looking at the IP header. That covers a lot of ground, and a lot of networking gear will do that. Then we put our software layer on top of it, the network virtualization platform, NSX, and then we produce these decoupled virtual networks in software, and these virtual networks are completely independent of the underlying hardware. You can create a virtual network, you can snapshot it, you can move it somewhere else, you can swap out the physical hardware and maintain your virtual network abstractions. So it's completely decoupled from the underlying hardware, and very importantly, it's a faithful reproduction of everything you would expect to get in a physical network, which means we didn't just give you an address space to play with, we gave you virtual addressing, we gave you bridging, routing, firewalling, load balancing, etc. It's all the services you expect from a physical network are reproduced in the virtual network. Those are the two things that I think are fundamental about network virtualization. You'll see why I stress that point in a minute. This is the platform. Hopefully you've seen a few slides like this before. As you know, we support multiple different hypervisors. We run a VSwitch in every hypervisor, and the VSwitch is the place where we can instantiate virtual network state, but we actually create virtual network state in the controller cluster, and that's sort of the source of truth for the virtual network state. And the job of the controller cluster is to attach virtual machines to virtual networks, to manage virtual network state, to receive northbound API requests from some outside system, typically a cloud management platform like vCloud Automation Center or OpenStack. Those API requests create logical networks with L2, L3, L4 through 7 services. Those API requests attach virtual machines to those virtual networks, and then the controller cluster reaches down into the vSwitches, creates the appropriate forwarding state to instantiate those virtual networks. If a virtual machine moves, the controller cluster is aware of that. It goes and programs a new virtual switch to take up the state where it needs to be as the virtual machine moves. So it maintains these abstract virtual networks even as things change in the physical world, as, for example, you move virtual machines around. This is all done in a way that's decoupled from the underlying hardware. So to do things like isolate the address spaces of the virtual world from the address space of the physical world, we encapsulate packets in a tunnel header as they go from one hypervisor to another. This tunneling protocol is something I'll talk about later, but today by far the most common tunneling protocol is VXLAN. At some point you need to get out of the virtual network, and so we have the NSX Edge, which can terminate tunnels and map virtual traffic onto physical interfaces so that you can bring traffic, for example, from a physical server into a virtual network. We also have a number of hardware partners, and I'll be talking in more detail about this. Our hardware partners also have equipment that terminates VXLAN tunnels. Under the control of the NSX Controller, we can program these third-party pieces of hardware to map traffic from physical interfaces into virtual networks and vice versa. That is the NSX network virtualization platform described in less than 10 minutes. So this is where we get onto more advanced topics. Any questions before I move on? Don't be shy. All right, good. You all understand the basics. You're in the right session. So, on to technical topic number one. This is how we connect virtual networks to physical devices. And you remember I said earlier that we have two different ways of doing this. We can either do it through our own x86-based appliance, or we can do it through third-party hardware. I'm going to focus on the third-party hardware. That's been the project that I've been working on for the last couple of years. And the reason we do this is primarily twofold. It's partly because some customers require very high throughput. You can get a lot more throughput out of a single, say, top-of-rack switch than you can out of a single x86 appliance in about the same amount of physical space. The other reason is port density. Some of our customers have racks and racks of physical equipment that they would like to connect into their virtual networks. For example, database servers that have not been virtualized for reasons that I don't understand. When they have these legacy devices they need to connect into virtual networks, you don't want to give up all of the agility benefits that NSX brings to the table, so you still want to be able to go into the controller cluster and create a virtual network, but this virtual network should have virtual machines and physical machines on the same network. So we can do this today by using the NSX API to create networks that look just like that one. And when we do that, what happens is that the controller receives this API request, and then it calculates what the top-of-rack switch needs to know, and it communicates with the top-of-rack switch using a protocol called OVSDB. By the way, before I go on, how many people heard me speak last year on this topic? Not that many. Excellent. Well, these slides are almost verbatim from last year, but almost none of you know that. But I am going to talk about some new stuff, trust me. So we have this database running on the third-party switch. And this database uses a somewhat obscure protocol called OVSDB. It's the Open VSwitch database protocol. Happens to be the database that's used for configuring Open VSwitch. It's an open source thing. You can go to openvswitch.org and download all the code to stand up your own version of the Open VSwitch database, which in fact is what most of our partners do. They download the open source implementation, they put it on their switch. And this database is now the meeting place for the controller and the switch to talk to each other. So what we're trying to do here is we're trying to get the switch and the controller to have a common view of this virtual network so that packets can flow between the physical and the virtual. So for example, the controller knows where the virtual machines are located, it knows the MAC addresses of those virtual machines, and so it is going to take what it knows and put it into the database. And similarly, the physical switch is doing traditional learning on its physical ports, and so as it learns physical MAC addresses, it writes them into the database. So this database has two clients, if you like, one on the switch, one in the controller, and so they both write what they know into the database, they both read what the other one knows, and eventually they build up a shared picture. And there's a lot more detail here that I won't bore you with, but eventually the physical switch knows everything it needs to know to set up its forwarding tables and to create VXLAN tunnels to the appropriate hypervisors, so that if you try to send a packet from a physical switch to a VM, it'll hit the forwarding table of the switch and then end up going down the correct tunnel and ending up at the right destination. So the thing to notice here is that everything that happened before the first packet was sent was a combination of API requests into the controller, followed by a control protocol exchange between the controller and the database. So we never had to flood packets anywhere to figure out where things were, because we knew enough at the different edges to reach a common understanding of where everything is and then program the top of rack. The only exception to that would be to try to find things in the physical world. We may still have to flood outbound traffic to discover things that are not currently learned by the physical switch. So that's a bridging example. The thing that we've started working on quite some months ago now, and we're making pretty good progress on, is moving up the protocol stack. And in fact, you'll notice a bit of a recurring theme in my talk today about sort of moving up the protocol stack. Remember when I defined network virtualization, about how we faithfully reproduce everything in the physical network? So I think like a lot of people, we started off thinking about, well, we'll do like virtual L2 segments, and then we'll do virtual L3, and now we're doing L4 through L7. So we've been doing that for quite a few years in NSX, sort of working our way up. You've no doubt heard a lot recently about, for example, micro-segmentation, how we're putting security services. So that's part of us moving up into sort of the L4 through 7 space. Well, here we're just moving up to layer 3 as we interact with the third-party hardware. So there's two things interesting about this example I'm going to work through here. The first is that we're moving beyond bridging to routing. The second thing is that it's a fully distributed implementation of routing, which I'll go through in a bit of detail, and it shows you how distributed implementations of many different services are implemented in NSX, and I'll show you why that's a good idea. But the main thing to know about distributed implementations is that many different entities will take place in implementing a particular function, like a router or a firewall, and there won't be any one single entity doing that function. And that provides a lot of scaling benefits, a lot of resiliency, and various other benefits too. So let me just move on with the example here. So on the left, the logical picture of the world. We're trying to create a VM in one subnet, a physical machine in another subnet. We want to build a logical network that routes between those two subnets. The physical picture is on the right, VM on a hypervisor, physical device connected to a switch. So we create that logical network by making API requests into the NSX controller, and it goes down and programs the vSwitches and the top of rack to instantiate this virtual network. And at some point, we're ready to send our first packet. Well, the first packet that's actually going to be sent will be an ARP packet, because the virtual machine in this example is going to try to talk to that physical server. And before it can do that, it recognizes that that physical server is on a different subnet. So it's going to ARP for its default gateway. It probably learned the IP address of its default gateway from DHCP. So assume we've got to that point, and now the virtual machine issues an ARP packet. By the way, I think this is the most advanced PowerPoint animation I've ever done, so I hope you enjoy it. So here's an ARP request coming out of the VM. It gets as far as the vSwitch. The vSwitch has been programmed by the controller to recognize this as an ARP heading for the distributed logical router. So the vSwitch catches this packet and replies. And it replies on behalf of the logical router. So now the virtual machine is perfectly happy. It knows how to get to the logical router. It has a MAC address to use, and it can send packets. So it sends its packet to the logical router, and it's going to hit the vSwitch. Now the vSwitch is going to have to ARP for the destination so that it can figure out what MAC address it needs to send the packet to, because we don't know that yet. So now the vSwitch issues an ARP request inside the VXLAN tunnel. It issues an ARP request on behalf of the logical router. It gets to the top of rack switch, which will now decapsulate it, take it out of the VXLAN tunnel, and forward it on to the destination as a perfectly correct ARP request coming from the logical router. So you can already see how the vSwitch and the top of rack are kind of collaborating to implement this logical routing function. Now the physical device just responds as it would. The ARP request comes back. It hits the top of rack. The top of rack will re-encapsulate this and send it back to the vSwitch. At this point, the vSwitch can populate its forwarding table, and we're ready to go and forward packets. And the packets, as they get forwarded, will actually undergo an L3 forwarding operation as they pass through the vSwitch in this example. So we'll see TTL decrement, we'll see the MAC address getting rewritten, all the things that a router would do. If you did trace route from the VM to the physical, you would see one hop in between being the logical router. So you might look at this and say, well, you know, the vSwitch is really doing all the work here. It's kind of the router. But if I were to turn around the packet flow and show you what happened when I went from the physical server back to the VM, the exact opposite sequence of events would have taken place. So all of that ARP resolution on behalf of in replying to the source would have been done by the top of rack. The ARP request to the destination would have been done by the top of rack. So the actual distributed router is fully distributed between the vSwitch and the top of rack. And if I were to build this out into a more complex topology with 10 hypervisors and 3 top of racks, every one of those would be taking part in implementing this logical router. So it's truly distributed amongst all of the devices that are affected by this logical router. So I think that slide has all the words that I just said. You can read it to check, but so you cannot point to any one device and see who's doing the routing because it's fully distributed. Distributed functions are super important. I already mentioned a couple of reasons. Distributed firewalling, I'm not going to spend much time on today, but that is a really powerful feature of NSX. And the fact that it's fully distributed not only gives you scaling benefits, but it also gives you the ability to be very, very sure that your firewall policies are correct, because you don't have to worry about whether packets are actually getting routed to the firewall. They always will go through because it's fully distributed all the way out to the VSwitch. Okay, so what I just described was one of the future things we're doing on the VTEP. I don't think I ever defined VTEP. Somebody in the front row must know what VTEP stands for. You don't? Okay. Somebody put up your hand if you know what VTEP. Okay. VXLAN tunnel endpoint. Sorry to call on you there. That's the risk of sitting in the front row. You look so knowledgeable, So it's VXLAN tunnel endpoint. So it's the term we use to refer to these devices that we control through NSX that terminate VXLAN. So a few things that we're doing going forward. We're developing bidirectional forwarding detection. Boy, I'll tell you what, one thing that makes this topic advanced. There's a lot of 3-letter acronyms and 4-letter acronyms in this slide. So bidirectional forwarding detection is something that we run across tunnels in the overlay today. So we're extending that to the hardware devices so that you can do things like make sure that if you are sending packets to a service node for replication, that you could detect the failure and move to a different service node, and also general health monitoring. We're talking with our partners about allowing the configuration of access control lists on physical ports under the control of NSX. So you could create distributed security policies that touch both physical and virtual devices. Also doing things like setting the QoS as packets come in from the physical world. And we're also starting to work with some providers of higher layer services, not just switches, but things like application delivery controllers, so that we could actually terminate VXLAN tunnels directly on those devices. So again, consistently moving up the protocol stack, as I said earlier. All right, so my second topic in the physical domain is about how we manage elephant flows. How many people have heard the term elephant flows before? Maybe a tenth of the room. Okay, so an elephant flow is essentially a high bandwidth, long-lived flow and that has the potential to cause congestion for other traffic. The classic sort of formulation here is that you have your elephants and you have your mice. The elephants are sort of these great big things that stomp on the little mice, and the mice are the low latency or the latency sensitive flows, not sending a lot of traffic, but sensitive to getting stuck in the queues behind the elephants. So what we've done in this whole space is to, first of all, decompose the problem into two pieces. First of all, if you want to do something about elephants, you need to detect the elephants. We're actually in a fantastic position to detect elephants because the VSwitch sees every packet that's coming out of a virtual machine. We actually classify them into flows already. And so all we have to do is recognize when a flow is both high bandwidth and long-lived. There's a few different approaches we can take to that, but the basic idea is you count packets per second. If you see that above some threshold for some duration of time, then you say, okay, that must be an elephant. And the great thing about this is that the applications don't have to know if they're producing elephants or not. You can implement this policy purely at the VSwitch. You might possibly want to have all the VSwitches report what they're seeing to some central place where you could actually make more intelligent decisions, but even doing it locally at the VSwitch works pretty well. So once you've detected elephants, then you want to do something to mitigate the effects of elephants. And there's, again, a large set of things we can do here, and by decoupling the detection from the action, we can effectively give ourselves a lot of ability to evolve different mechanisms. But we've prototyped a couple, and one thing that we did, which I'll show you in the next couple of slides, was when we saw an elephant, we set some QoS marking in the outer header of the packet. So in the VXLAN header, we would mark the diffserv code point to say it's an elephant. And then for every other packet, we would do nothing, so by default, everything else was mice. And then in the switches, we configured a couple of different queues so that the elephants and the mice would both go through the switch, but they would not interfere with each other from a queuing point of view. You could do other things, like if you were feeling really fancy, you could have a completely separate route for the elephants, send them off on an optical path. Any number of things could be done with the elephants, but essentially you want to prevent them from causing congestion for the mice. You can even take elephants and cut them up into subflows to effectively convert them to mice. Not something you should try in the real world, by the way. So the virtual world is so awesome. So here's what it looked like before we were doing anything. So what you see here, the green is the bandwidth being consumed by the elephants, and the blue is the latency being experienced by the mice. This is one of those great sort of Edward Tufte kind of things that shows so much in 2 dimensions. So what you see here is that the mice experience fairly high latency in the order of 3 milliseconds, I think that is, while the elephants are having a fine old time getting 950 megabits of throughput. And if the elephants were not there, as they are at the very end of the graph, the mice actually get like half a millisecond of latency. So the mice are clearly suffering because of the elephants. And then we turn on elephant detection, and you now see a very happy result, which is that the mice now see consistently low latency because they're now in a separate queue from the elephants. And the elephants still see consistently high bandwidth because the mice are not big enough to slow them down. And so it's a total win-win that we just by putting these 2 classes of traffic in different queues, we've got the elephants what they need. They can't be latency sensitive because they're sending so much traffic it takes them a long time to complete anyway. But the mice, you know, on average are latency sensitive, so we've given them what they want, we gave the elephants what they want. Something for everyone. So that's it for the physical network. So now I want to move on to talk a bit about tunneling. As I said, it's a subject dear to the heart of traditional networking people. I do want to stress that in the big picture of things, the tunneling protocol doesn't matter that much. I'd kind of like to have back the number of years I've spent arguing about tunneling protocols and in general about packet headers, but you know, it's water under the bridge. So, gosh, that was a horrible choice of analogy. So the tunnel format is actually an important detail, which is why we spend so much time arguing about it. So it turns out there's kind of a large set of things that we're trying to optimize when we design a tunnel header, and it's very hard to get them all at the same time. So you want interoperability. For example, we use VXLAN to get from hypervisors to top of racks. Interoperability between hardware and software. You want to get equal cost multipath, so you have to make sure there's good entropy in the header so that hashing algorithms work well. You want the thing to be extensible. We have been coming up with new ideas in network virtualization at such a high rate in the last few years that we have our own header that we invented at Nicira called STT. We stick a new bit in there, it seems like every month or two, because we thought of some new feature. So extensibility is extremely valuable, but of course that header we invented at Nicira completely fails on the interoperability front. Performance is one of the things we optimized with STT. It's been less optimal with things like VXLAN, although that is in the process of getting fixed. And then you want visibility. You want to be able to see what's going on. So if you go and stick Wireshark on a link, you'd like to be able to figure out, you know, what's going on behind that encapsulation header. So there's no perfect encapsulation out there today. And so like all good sort of standards people, we said, well, there's multiple competing standards. Let's unify them all by creating one more competing standard. I see a few people have been to standards meetings. I kind of wish it didn't have to be that way, but it is where it is. So we created this new protocol, and I'm happy to help all the people who've been worrying about how to pronounce this protocol. We pronounce it Genève. If you've ever been to Switzerland, that's the way a French person with an Australian accent would say the capital, or is it not the capital? But anyway, Geneva in French is Genève, and it stands for Generic Network Virtualization Encapsulation. I was pretty proud of coming up with that. And then, we got support from most of the big players in the x86 world behind this protocol, which may tell you something about where we are in the life cycle of this protocol. It does provide all of those features in the previous set of bullets, but not yet a lot of interoperability for existing hardware. So where does that leave us? Well, This is a picture I also showed last year, trying to help people understand that much as it is enjoyable to argue about tunneling protocols, it may not always be productive. Just as you probably don't spend a lot of time arguing about what type of cable is used in your data center, provided it's sort of compatible with the different endpoints, you shouldn't spend too much time arguing about your tunneling protocol. In a typical NSX deployment today, we see things like this, where we use STT between hypervisors and VXLAN from hypervisor to third-party hardware. We support quite a few different ones today. For us, it's a fairly low-level detail that we sort of create the binding. At the very last instant, as we send a packet out, we say, oh, better put that header on it, having done all the hard work in advance. So Genev could easily come in quite quickly for hypervisor-to-hypervisor traffic because we control that software, we can update it quickly. It's going to take a little bit longer before we get third-party hardware that supports Genev, but at some point, you could start getting Genev running there as well. So I'll come back to the issue of where this is going to go in the future. First of all, I just want to spend a couple of minutes showing you a packet header. Again, I love to get these pictures in for the hardcore networking people. So Genev, like VXLAN, sits right behind a UDP header, so you get the standard IP encapsulation for things like equal cost multipath, the ability to go across any IP fabric. The main difference between Genev and VXLAN is the presence of options. And options are the key to providing extensibility, which particularly in a software world is super important. So we really wanted to keep this feature of STT, and of course any hardware that doesn't understand those options can easily punt it and not process it. We even have a way of saying whether options are critical or not. The options are type length value encoded, makes it very easy to skip anything you don't understand. As I say, there's a bit to tell you if they're absolutely critical. And there's lots of different things that you can do with these options. So for example, in logical space, sometimes you send a packet somewhere other than its true destination. So for example, you might mirror packets to a collection engine. Well, you want the collection engine to really know that packet's for him, even though his MAC address is not in the destination. So you can put that in a field in the encapsulation header. We do a thing called trace flow. It's a way of sending synthetic packets through a virtual network to figure out where are things going wrong. So just a single bit could say, this is a trace flow packet, please let me know what you did when you processed this packet. We can do things like egress policy based on where did the packet come in. And then things like state versioning, for example, changing the state in a synchronized way between both ends of a tunnel. And service chaining is something I'll talk about later on, but it requires you to do things like passing metadata from one end of a tunnel to another. So, et cetera is kind of the key word here, which is that we come up with new ideas all the time. This is the beauty of network virtualization, is we don't have to be tied into what we can get in hardware today. But what about hardware, and what about the existing encapsulation? One of the concerns I hear people say is, so are you telling me I should wait before going and buying some VXLAN capable hardware? So the answer to that is no. Please go and buy some VXLAN capable hardware. There are a lot of vendors who will happily sell it to you, and it will continue to interoperate with NSX probably long after I retire. Now, you don't know when I'm going to retire, but I think it's going to be a while. So again, take that for, we have no reason to deprecate VXLAN. It's a very fine protocol for doing what it does. As I said, we'd like to do a few more things, like have extensibility. We have STT today. STT will also be around for a while. It's a super high performance, flexible protocol, works really well between x86. It's really easy for us to have multiple protocols. We do it today. There's no reason for us to stop. So if you were to go and buy a switch today and you were worrying, what should you do? My advice to you is very simply, get one that terminates VXLAN, and preferably one that interoperates with NSX, which leaves you a pretty wide range of choices. Of course, if you're buying your underlay fabric and you don't actually care about all the hardware termination that I talked about earlier, then all you really need is a switch that forwards IP packets. And there's an awful lot of those you can buy. So, you shouldn't really worry about this, new emerging, not yet even close to being a standard thing called Genev. The really main thing we were trying to do here was we're trying to make sure we don't have to keep on inventing new encapsulations every year or two. We think that Genev, because it's so flexible, will let us keep on doing that. And so that's really our hope. Okay, enough about tunneling protocols. Let's talk about service chaining. I'm going to take a break again and see if anyone wants to ask a question, just to see if anyone's awake. Here's a question. Could you go to the microphone? It's a short walk. This gives time for somebody else to work up the nerve to ask a question. Sorry, I should have had some. Okay, go right ahead.
Yeah, question is about security perspective, like ARP inspection, DHCP looping, source guarding, all those very basic security, but I think it's very fundamental.
Yeah, so I think the question is kind of a broad one about sort of the security perspective on NSX. In general, the number one reason people are deploying NSX today, I would say, is because of its security features. I certainly don't have time to go into that in great detail. There's a number of good sessions on the security features of NSX, but one of the things to realize today is that we don't encrypt the traffic, generally. We can encrypt traffic across the WAN, but inside the data center, we don't encrypt the traffic. So certain types of attack in the data center, if you have physical access to the data center, certain things are possible. But most kinds of attack are extremely difficult because it's very, very hard to inject a packet into the network, even if you had access to the data center. It's also very, very hard to get control of the controller because it doesn't execute arbitrary code. It doesn't provide a lot of points of entry. So the product is quite seriously hardened. But in general, one of the things that we do with NSX is we create networks that are isolated from other networks. And so we actually, we're enabling this thing called microsegmentation, which isn't on my script for today, but it's a super important aspect of NSX. The idea that you could, if you want, put every virtual machine in its own isolated network. You can put a firewall rule in place for every single virtual machine, should you want to do that. And you can even do this in a way that's reasonably scalable. So some of our customers are implementing zero trust networks, which means you basically assume that every virtual machine is going to get compromised and treat it as such. And you can build networks with NSX because it's so easy to deploy security policies by saying something centrally at the API level and getting it pushed out in a distributed fashion. So it's probably more than I have time to say about security, but it is a great aspect of the platform that I wish I had more time to go into more detail. If you haven't seen a presentation on Goldilocks, which is our new sort of strategic thrust around security, I'd say you should definitely see if you can see one maybe this week or maybe catch a recorded one online. Okay. Pardon me. So my virus protection is not up to snuff, I'm afraid. So service chaining. So what is service chaining? I'm actually on a bit of a mission to try to change the term from service chaining to service graphing. Because the idea really is with a service chain, you're actually creating a topology of services. You want to take a packet, put it through a function, send it to another function, send it to another function, and exactly what sequence of functions it goes through may depend on decisions you made earlier in that chain. So the chain may actually be not a straight line, but a more complex branching tree. And so lots of different things can be put into these service chains, and this is really a sweet spot for network virtualization. Our whole business has been built around building virtual topologies very quickly and very cheaply. So the idea of creating something that takes something like an SSL termination engine, a firewall, a WAN optimizer, a load balancer, and puts them into some kind of topology, that's exactly what we do with NSX. One of the things that you often want to do with service chaining is you actually want to pass metadata along the chain. So for example, I might have a very complicated classifier at the start of a service chain that does some kind of user authentication, figures out who you are, figures out what class you belong to, and decides, 3 hops further down the chain, I'm going to give you a particular class of service. You'll get the WAN optimizer, but not something else. And so you want to do classification here and then pass the result of that classification through to some other box in the chain. So that's something that Genev actually provides a great place to put metadata. Metadata, data about data, basically means you have to carry information alongside the packet. You can't put it in the packet because then it would be data. So you have to put it outside the packet in some kind of header. And existing headers often don't give you room for that. Genev, being so extensible, does. Oh, my slide just advanced itself. Interesting. So here's an example of service chaining. using our distributed firewall as an example, so on the top, I've got a couple of different boxes, a web VM, an application VM. I want to route between them, and I want to send the packets into a firewall and out again. So the service chain is basically web, router, firewall, router, app. And so that's the logical view of the service chain. The physical implementation of it is shown at the bottom, where we take a web VM, we connect it up to one hypervisor, we put the app VM on another hypervisor, and the entire implementation of that service chain is implemented in the distributed VSwitch, in the VSwitch, which implements the distributed routing function and the distributed firewall. The other thing we can do here is we can insert third-party functions here, and you may have heard about our integration with Palo Alto Networks. We're doing this with probably a dozen or more other partners, where we can take some packets as they go into the vSwitch and the firewall, selectively redirect packets to a third-party service. So for example, one of the things we do today is we say lots of things can be figured out that you just want to drop the packet. Don't emit packets if they're going to this IP address. Don't emit packets if they're going to this port. Don't emit packets if the TCP connection hasn't been established properly. So you can drop a lot of packets using the native firewall, but the Palo Alto firewall goes a lot deeper into the packet. So for some packets that are sort of a gray area, send them off to this guest VM and have them do a deeper inspection and have them come back and tell us what to do. So this is an example of service chaining that's actually in the product today, whereas the Genève piece is a bit more forward-looking. And I can see a question lining up at the microphone there.
So there's an alternate approach in the industry that proposes to do service chaining with a generic shim header that could be stuffed between the payload packet that you're trying to chain and anything else. Could you comment on that approach versus putting the metadata into an NCAP like Genève?
Yeah, so the comment was that there's another approach kind of floating around the industry about this sort of generic service chaining header. It actually looks extremely similar to what we would do in Genève. Genève is basically a shim that sits between the IP layer and the encapsulated packet, and we could take the exact format and semantics of the header you described and put it in as a Genève option. So at this point, this is one of those kind of computer sciencey things. It's like there's only so many places to put the information. We're just arguing about the layout of the bits in memory. Okay, I think the man was nodding, so that's probably a good sign. Okay, so my last topic before I wrap up and open it up to final Q&A is I want to give you a bit of a flavor of where we're going with multi-site network virtualization. So there is a session which I think actually happened earlier today called multi-site scenarios or something, and it's NET1674. Obviously, you can't go and see it, but you can get the slides and the recording probably the end of this week. So that will kind of give you a fairly 1 hour deep dive on what works today in terms of multi-site virtualization. So as I said, most of our deployments today are actually single site, but there are things that work today. For example, you can take an NSX cluster and stretch it across multiple data centers in a metro area. You can also do something that I consider totally cool, which is you can snapshot a running virtual network in one location and move that snapshot or clone it and move it to another location. This is a great use case for, say, testing things out. We've actually taken a customer configuration, snapshot it, move it into our lab, make some changes, confirm the changes do the right thing, send a new snapshot back to the customer, and they run it in their network, and they know that it's going to work. So that's an example of like moving network state from one place to another. You can fairly easily think how a similar kind of technique could be used for disaster recovery. You snapshot your network state every 15 minutes, mirror it to another site. Hey presto, you've got a disaster recovery network ready to go if you ever need to bring up that other site. So lots of things are possible today. Mostly what I want to do in the next sort of 3 minutes is just give you a sense that this is a pretty complicated space, and so you need to think fairly hard about what you want. And sort of my sort of least favorite question is, can you please help me stretch layer 2 between my two data centers? Not that that's necessarily a bad idea, but you want to think very carefully about whether it's really what you want. If you stretch L2 between two data centers, you probably want to think about, if I move a VM across that L2, where's the storage for that VM? Did I also replicate the storage? How is the routing going to work? A packet's going to show up in the old location and then have to get sort of hairpinned across. So I'm not going to give you any answers today. I'm going to encourage you to sort of think about what you want in the multi-site space. I'll just say a couple of things about where we're going here. I like to think of many things in sort of being on a spectrum. This is one of them. There's sort of one end of the spectrum, which is start with a single data center, and imagine that data center gets very large. So you'd like to take an existing NSX deployment and break it up into multiple deployments, but still have them be federated in a way so that I could build virtual networks that span across those multiple clusters of NSX. That's what we think of when we think of sort of federation of NSX. This is something that our largest customers are looking for so that they can have a fault domain of a certain size that's smaller than an entire data center. In this environment, of course, latency is very low, bandwidth is very high. You have certain constraints that you can work around there. The other end of the spectrum is where we've got data centers separated by very large distances across the different continents or opposite sides of a large continent. Then you see sort of 100 millisecond latencies, not so much bandwidth, and we have different kind of ideas about how to tackle that. And then the metro space kind of sits between those two. So let me talk about the Geo Case first. This is another slide that I pretty much used last year. Unfortunately, it's still in development, but it's getting there, closer than it was a year ago. So what we've done is we've started developing some capabilities to connect virtualized data centers to MPLS networks, specifically in the wide area. And this turns out to actually be a pretty good building block for building multi-site solutions as well. So what we do is we treat the interface between the data center and the WAN as an inter-autonomous system interface. And given the time, I'm not going to spend a lot of time explaining what I mean by that, but there's an RFC that tells you everything you need to know, and you're all advanced, so you can go and read that. And then we advertise prefixes between the data center and the WAN using multi-protocol BGP with some of its MPLS capabilities. And what we basically do in the data plane is we label packets from different virtual networks with different MPLS labels. So the fundamental problem we're solving here is we can have many tenants or many isolated networks at the data center, and we can advertise them out into the WAN in a way that they're isolated from each other, and we can tell them apart both in the control plane and in the data plane. Now, if you take this and instead of connecting it to an MPLS WAN, you connect two of these things back to back, you've now got two data centers where I can create virtual networks in one and have them automatically reachable to the appropriate tenant in the other data center. And so now what I do is I come into here, I create a virtual network, looks something like this. I go over here, I create another virtual network, and these could be two completely separate cloud management systems doing this, provided we have some way of identifying that there's a common tenant on both sides, or perhaps in an enterprise case, a common application domain or something. So I create a virtual network on that side, and then multi-protocol BGP advertises the prefixes with a particular set of tags across the WAN. This could be done. You don't need MPLS in the WAN. This is just you could do this with a tunneling approach across the WAN. And now we've basically made these two virtual networks aware of each other, so they remain isolated from all the other networks, and yet you've now extended a virtual network across the wide area. So that's a thing that I think will actually get done this year. See me in a year and see if I was right. The final thing I want to talk about is, again, reusing some material you may have seen before. Today, the NSX Controller is a very effective distributed system. Every piece of state is either replicated across different nodes in the controller or split across different nodes in the controller. So in a three-node system, we sort of distribute state like this. So there's sort of some persistent storage across all the different nodes to keep track of desired configuration state. But something like the state of a particular hypervisor is stored in one node in the controller. When we get to bigger deployments, we spread the state out across more nodes in a controller cluster. And the amount of traffic between the different nodes in the controller cluster is fairly moderate. Depends on what's going on at any given time, but typically we break up the state in a way that provides pretty good isolation between different nodes in the controller cluster. So it's actually not that hard to think about splitting the controller cluster into two parts and putting, say, one subcluster in one data center, another subcluster in another data center. And then you could build virtual networks that span the two data centers. There's a lot of detail that I'm skipping over here. the amount of communication between the nodes is still quite a bit more than you would get just using a routing protocol, because you'd be carrying things like the state of firewalls across the different controller nodes. If a virtual machine moves from one data center to another, a fair amount of state is going to potentially get moved from one controller node to another. So this is definitely more of a metro kind of approach than a geo-distributed approach. But this is another thing that we're working on. I'm not going to make such a confident prediction about when this will show up, but this is our high-level approach on doing very rich semantics across multiple data centers in a moderate geographic area. And that brings me to my conclusions, fairly timely. So hopefully, I didn't really stress this today, but hopefully you've already figured out this week that network virtualization is not actually a bleeding-edge technology anymore. You know, Pat Gelsinger announced a month or two ago 150 customers have bought NSX. We're getting an increasing number into production. And it's not just the huge people anymore who are doing it. So, you know, hopefully you understand this is not something you need to be scared of getting involved in. I spent a fair bit of time today talking about physical networks. You know, sometimes people think that network virtualization is trying to do away with physical networks. Nothing could be further from the truth. We've worked very hard with almost all the switching players in the industry, even some that we haven't announced yet, to make sure that we make the best usage of the physical resources that are underneath, just like we work a lot with the server folks to make sure we take good advantage of what they provide. And you know, you've seen us do things like, you know, like building a system for moving virtual traffic into the physical world and vice versa, dealing with congestion in the physical network. We've talked a bit about tunneling. You know, I just wanted you to take away the fact that you shouldn't be too alarmed. It is kind of a detail. It's an important detail. You know, lots of engineers need to think about it, but you shouldn't let it worry you from a deployment point of view. It's very easy for us to manage those details pretty much under the covers. Somebody asked me earlier today, is managing thousands and thousands of tunnels a problem for NSX? Certainly not something that keeps us awake at night. Like, it's hard to build a scalable controller. You know, we have deployments with tens of thousands of virtual machines on a single NSX controller across thousands of hypervisors. There are some challenges in building a system that scales that well. Maintaining a few thousand tunnels is not one of those challenges. So, you know, don't worry too much about tunneling. And then, you know, I talked a little bit about multi-site. You know, it was pretty high level, but I just want to give you a sense that we have some solutions today. There's actually design guides coming out. We also have a plan going forward about how to tackle the different use cases. And you know, you do need to think fairly hard. So this is a sort of a good discussion to have with your SE if you're getting to the point of thinking about multi-site. But it's, for most people today, this is still a forward-looking topic. And I think it's a super exciting time for networking. You know, I've been doing networking for 25 plus years. I think this is the biggest transformation I've seen in networking. I mean, I was there when, you know, ATM was in its ascendance and when it crashed. That was fairly exciting. I was there when you know, tag switching was invented and then turned into MPLS. I had a little bit to do with that, but I'm not the inventor of MPLS, contrary to what you may have heard. But you know, I've been involved in some exciting things. I don't think there's been anything more exciting in the last 25 years than what we're doing today. So I hope, you know, you're a lot of our most loyal customers here. I hope you're excited about this, and I hope you get a chance to play with NSX very soon. I'm just going to mention before I close, well, I'll say thank you, but then I'll say some other things. Whoa, I guess I lost my last few slides. Well, never mind. Okay, what I was going to say was there are other sessions you could see on NSX. Apparently, I'm not going to tell you what they are, but there's a bunch of hands-on labs. The hands-on lab last year for NSX was, by at least a factor of 2, the most popular hands-on lab. So if you're really interested, totally do the hands-on lab. But there's a lot of other sessions you can go and learn more. Some of them will probably go deeper than I did. I hope you got something out of this session. Thanks very much for your time.